So I'd like to welcome everybody to the next to last ecology seminar of the year. Next week is the Merton Love Award speaker, Connor Taft. And so I just wanted to remind everyone of that. And before we get started today, again, too, I'd like to acknowledge that today's speaker is sponsored by the Storer Endowment, which brings in speakers in the biological sciences to the campus all year long, in particular very distinguished speakers. And our speaker today, I'll give a very brief introduction, because I'm sure you'd much rather listen to Joel Cohen than to me. Joel is in the Laboratory of Populations at Rockefeller University. Actually, he's the only faculty member in that Laboratory of Populations. He also has an affiliation with Columbia University. His contributions to ecology and to theoretical ecology are vast and broad and extraordinarily influential, in particular in areas like food webs and a number of other areas, demography. And today he will be talking to us on abrupt, well, you can read that as well as I can say it.
Thank you very much, Alan. Can you hear me in the last row? Yeah, good. If my voice drops too much, start waving so I get some signal that I'm not communicating with you. Thank you for coming out this beautiful afternoon to be indoors. I'm sorry about that. And I'd like to thank the people who spent part of today with me. I had some fabulous conversations all day today and yesterday as well. I am really grateful for the conversations I've had with people here. Well, what keeps an old guy like me going? It's surprise from my own work. And the story I want to tell today is about a surprise that I encountered while quietly minding my own business in the course of some theoretical research. It may turn out to be interesting to other people too, that remains to be seen, but it was incredibly amusing for me, and I want to just tell you this story. So my title is, I'm assuming that everybody here can read, and so I won't actually repeat the title. 3 parts. I want to talk about abrupt biotic change. 2, about Taylor's law. 3, abrupt biotic change in theories of Taylor's law. Abrupt biotic change. Whether a change is abrupt or not depends on how fast you're watching. If you take an egg and sit it on a table and push it off the edge, you'll have a splat on the floor pretty soon. If you come back, if you only observe the system at intervals of 1 hour, that looks like an abrupt change. If you take a very high-speed camera and photograph the process, it's a smooth change on the scale of microseconds. So we're talking about a scale-dependent observation. You can have abrupt biotic change under 3 classes of environmental behavior. 1 is no behavior, remains constant. 2 is the environment changes abruptly. 3 is the environment changes smoothly. I'm going to give examples of all 3, and I'm going to focus on this last for most of the talk. So here's an example of abrupt biotic change in a constant environment. And it has to do with a model of punctuated equilibrium in a fixed fitness landscape. I don't know if you're old enough to remember punctuated equilibrium from the days of Steve Gould. Well, we showed that ordinary neo-Darwinian evolution can account for punctuated equilibrium. This is a paper in Nature in 1985. So here's the fitness landscape. At 0, there's a little peak, and then there's a valley on either side, and then there's a bigger peak over there at 3. This is some trait that you measure in an organism. And you have genetic drift And we modeled that by saying that the change here is the sum of the slope and some small scalar times something that's either plus 1 or minus 1. So when the slope is positive, the thing wants to go back toward its nearest peak. When it's negative, it wants to go in the other direction. And what happens is if you start the system here, you can simulate this equation on any computer. It's very, and in fact, that's what this is. It starts here and it wanders around, and it wanders around, and it wanders around. Finally, it starts moving very fast, and it goes downhill and uphill at exactly the same speed. And that's something you can prove analytically. That was proved quite a long time ago. You go down this hill and you zip up the other and you move to the other peak. So it looks like you have a discontinuous change, although at fine enough time resolution it's a smooth change and it obeys traditional Mendelian genetics. There's nothing unusual about it. And to illustrate the phenomenon, over here is an experiment in selection for scutellar bristle number in female Drosophila. This is the number of bristles, and this is the generation. And what you have is you start from the normal here, you stay here for a while, and then you have an abrupt transition as a model. So nothing has changed. It's just random walk in a fitness landscape. That's the first kind of abiotic change in a constant environment. Secondly, you can have an abruptly changing environment. So if the environment hits the system with a hammer all of a sudden, you do expect change. And this is an example, this is a plot of the percent of readily fossilized marine animal genera that were extinguished per unit of time over the last 500 million years. And this used to be called, when I was in school, the KT boundary, when the meteorite came and hit. But it wasn't, at this point, 75% of the species were lost. It coincides with the Dakin flows, those enormous volcanic eruptions which darkened the skies for several years. There was an impact, an iridium anomaly, and marine regression, meaning that the land was coming up and the seas were going down, and so you lost a lot of species. So there was a huge, 75% of the species were lost about 65 million years ago. That doesn't seem to be a theoretical problem. If you hit something with a hammer, either it will ring or it will break. And this is an example of that. So what I want to focus on is abrupt biotic change in a smoothly changing environment. And a prime example of that is in the paper in Quaternary Science Review by Domenical and colleagues in 2000. And I presume that you know that the Sahara Desert, until a few thousand years ago, had lots of rivers. It was a lush, tropical landscape. We find hippopotamus bones in riverbeds that are now completely sand. It was a beautiful place to be. And there was a gradual decline in the amount of sunlight, this is radiation forcing, that came in, which drove a monsoon up across the Sahara and deposited moisture, rainfall, onto this tropical landscape. And at some point about 5,500 years ago, there was an abrupt drop. The monsoon wasn't strong enough to bring the moisture, and consequently the vegetation cover of the Sahara dropped very dramatically. How do we know that? Well, Domenical and his colleagues took cores off of West Africa from the ocean floor, and they measured what fraction in each little, they were able to slice it so that you get a 100-year resolution. Every 100 years you could count what fraction of the deposition came from the land mass as opposed to the sea animals that were living over that spot. And notice this goes from 40 to 60, so it's increasing this way. The amount of material that originated from the land abruptly increased here. And the grams of material that came from the land per square centimeter per 1,000 years also abruptly increased at this point. So as the vegetation cover disappeared, the dust was depositing more material into the sea. And that's the trace that we see. So there was a very abrupt transition in the biotic community in response to a smooth change in the abiotic community. And shortly after that paper appeared, there was first an influential paper, Catastrophic Shifts in Ecosystems, Nature 2001, followed up by a review paper 2 years later by some of the same authors. Steve Carpenter, I guess, was a lecturer here in the same the Storer lecture series not too long ago. Catastrophic regime shifts in ecosystems. And in that latter paper, in both of these papers, they talk about, well, you could have an ecosystem state that varies smoothly with environmental conditions, or it could vary smoothly and then go down this slide, rapid change as environmental conditions change slowly, or you could go along this surface and then drop off to a lower branch of this surface. And as an illustration of this, I took a picture from a report published last year by the National Research Council on abrupt change in the circulation of the ocean. So the Atlantic meridional overturning circulation is a $2 word for what most of us think of as the Gulf Stream. And the Gulf Stream, actually the Gulf Stream refers to the part that's along the coast as opposed to the whole conveyor belt. It takes a stream of salty, warm water that moves from the tropics north along the west coast, the west of the Atlantic, and as it moves further north, it gets colder. And as it gets colder, the fresh water evaporates, and because it's warmer than the surrounding, the fresh water evaporates, it gets colder, it gets denser, and when it gets to a certain point in the north, it sinks, because salty water and colder water is denser than the surrounding water, and it goes back along the ocean floor to the tropics and rises again. And you have a conveyor belt that moves heat from the tropics to the northern latitudes. Well, how much salinity you have in the water as it moves north depends on the freshwater runoff into the Atlantic Ocean. So if there is more water melting from ice in the northern latitudes and more water precipitating and running into the ocean, you don't get the density difference that you need to make the thing sink. So you could go, this is NADW, is North Atlantic Deep Water Formation. That is how much water is sinking per unit time. And this is how much fresh water we have now at zero. This is a schematic diagram. We're up here. Depending on exactly where the water gets dense enough to sink, you can get two different responses, either up there or up here. But in any event, when you come to the edge here, if you started putting in more fresh water, the system would drop to a lower branch and you would have no North Atlantic deep water flow, which would mean stopping the conveyor belt. And that would mean that you would not have this flow of heat from the tropics into the north. Okay, so this is to show that there's a conceivable mechanism that could implement this schematic situation. And then there was a question, well, how can we know if we're about to approach such a situation? And there was another paper by the same authors, Sheffier and a whole bunch of other guys, including Steve Carpenter and George Sugihara, saying, complex dynamical systems, I like it, I should have violins and cellos in the background, ranging from ecosystems to financial markets and the climate, can have tipping points at which a sudden shift to a contrasting dynamical regime may occur. This is true, but whether or not they're, well, it would be nice if we knew it was coming, is what they're saying, and I agree with that. But then Alan Hastings, right here in the front row, and Wisham, who is a student of yours, is that right? Postdoc. Okay. Said, well, yes, but you can also have regime shifts in ecological systems with no warning. And there's a set of ecological models that have this property, and therefore there are probably also natural systems for which there will be no forewarning of a regime change. That was a very healthy paper. It says, you know, models can go one way or the other, and we should be looking into it. I found this motivating, and this is a very recent paper. Here we review evidence that the global ecosystem as a whole is approaching a planetary scale critical transition as a result of human influence. I consider that to be a tendentious statement trying to raise alarm rather than a fact-based statement. But nevertheless, it may be even, they might be right, we don't know. However, I agree strongly with the conclusion we need to improve biological forecasting by detecting early warning signs, if they exist, of critical transitions on global as well as local scales. So that's the search here. Finish part one. You now are experts on abrupt change. Part two, Taylor's law. Well, suppose we have a bunch of observations of population density. That is, I've got a patch here, I measure the population density there. I've got another patch here, I measure the population density there. I've got another patch, and I measure population density. Those are our numbers x1 up to xn. And people usually assume that these are independent, and that assumption is not tested. X could measure trees per hectare, bacteria per ml, people per square kilometer. This is how we compute the sample mean. I hope this is not news to you. This is how we compute the sample variance. If there is an underlying distribution, it has a population mean and a population variance. The sample moments always exist. Population moments, these things, the expected value of this and this, the expected value of that, may or may not exist. You know that there's something called the Cauchy distribution. It looks perfectly nice, like a bell-shaped curve. It has no mean and it has no variance. But you can always select n observations and you can construct a sample mean and a sample variance. So I'm going to be naive about this and talk about the sample mean and sample variance most of the time. This is Roy Taylor, and he founded and read the Rothamsted Insect Survey. They put up 800 balloons over Britain and did insect traps in the air to study the movement of insect pests from the continent across Britain. They were able to save Britain millions and millions of pounds by timing the spraying of the barley crop for pests only when there was a problem. They deferred spraying because they could tell exactly when it was coming. And, you know, they do a lot of beer in England. And they drink a lot of beer in England. And it's good beer. And part of it is that they have these entomologists from Rothamsted helping them protect the crop in the most efficient way possible. So operating these balloons actually ended up to be a big saving for the UK. And he was president of the British Ecological Society. He published a paper in Nature in 1961 in which he said, in all the sets of samples, now watch the words, sets of samples, not one sample, x1 to xn, but a bunch of samples, okay? In all the sets of samples I have examined, variance appears to be related to the mean by a simple power law. Variance is proportional to a fractional power of the mean. Variance equals some constant a times the mean to the power b. where A and B are characteristic of the population in question. This is an interesting thing. Suppose you made all your measurements in insects per square millimeter, and then you made the same measurements in insects per square kilometer. It turns out that if you do the mean and variance and fit this law, you'll get the same value of B. It's scale invariant, because you can put any constant inside the M here, and it just washes out and moves over to the A. So B is independent of the scale of measurement. Taylor hoped that this B was a species-specific index of aggregation. That turns out to have been false. That is, the same species can have a different B in different places or times, and different species can have the same B. But the power law that he proposed turns out to be amazingly effective. It even shows up in data when I analyze it, which is very surprising. And this is from his paper. It's an incredibly badly done paper, and yet it is enormously influential. So he gives you 24 samples here. He does not tell you the sample size. He doesn't even identify the species for most of them. He gives these graphs for about 13 of them. The axes are not labeled very well. You can't make the connection between this and that. It's a catastrophe as a piece of science, but it's enormously effective because it's simple and it's got something true in it that works very widely. In the same year, unknown to Taylor, two guys in another island on the other side of the world, in New Zealand, published a paper, Heyman and Lowe, in the New Zealand Journal of Science. And they took aphids from hundreds of samples on different plots, different plants all over the place, and plotted the logarithm. So each dot here, this represents somewhere between 5 and 35 plants. And they counted the number of aphids on each of these, and they calculated the mean and the variance in those plants. And then they did this in another field here and another field here, all the way up. 182 sets of aphid plants. And they used a much better regression method that recognizes that the sample mean is not given with infinite accuracy. In ordinary least squares regression, you assume that the x-axis is known perfectly. That is not true if it's a sample mean. So your regression techniques should take account of that. It turns out, because this is such a good linear relationship, it doesn't matter what technique you use, you get almost the same estimates. But they did a sophisticated job. This is a much better paper, and it is completely unknown. Very few people have ever seen the paper. I was lucky enough to find it in the library, sitting on the shelf at the University of Chicago, New Zealand Journal of Science, 1961. This is from an early paper by Taylor and colleagues in 1980. So aphids do this all over the world, but different species have different slopes. This is one species, this is another species, a third species, and there's a range. This line here has slope 1. That is, if you move left 1 block, you move up 1 block. And that's to show you what you expect if individuals are randomly distributed in space. In the Poisson distribution, the mean equals the variance. Mean equals variance. That means the variance equals the mean, which means the variance equals the mean to the 1 power. So if you take the logarithms, you get a straight line of slope 1. Okay? And that is what this references. The point being, most of these are not randomly distributed, they are aggregated. This pattern of relationship between the variance and the mean became known as Taylor's law. It has a simple common structure. Blocks are a block of observations would correspond in this picture to one of these dots. One of these dots. And each block has a mean and a variance, and now we look across all the blocks and we examine how they're related. The definitions of blocks the labels we put on the species, the moments, whether we use samples or population, and the weights may vary. It applies, there are 1,000 papers on Taylor's law in the ecological literature. It has been tested for hundreds of species, somewhere between 400 and 500 species. It applies very widely. It also applies to cells per organ in 178 species. Okay, you count the number of cells in the pancreas of 100 different mice, and then you do it in the cells, and you take the mean and the variance of the number of those cells. You take the mean and variance of the number of cells in the heart of 15 different people, mean and variance. You plot all of these, you get a straight line with a slope about 2. Whoops. So it applies to a whole bunch of things, including single nucleotide polymorphism density, cases of measles and whooping cough, sexual partners of HIV patients, the rainfall at weather stations. The rainfall does not know about the other drops. So any model that makes behavioral assumptions about the particles interacting can't be true for the rainfall. It applies to packets switched in router interfaces. It applies to stock trades and currency trades. It even applies in number theory. So who cares? Well, applied insect entomologists actually used Taylor's law to define thresholds for sampling. Ordinarily, people assume that variance is independent of the mean. If you do an analysis of variance, one of the assumptions is that the variance is independent of the mean. If that's not the case, you will draw wrong conclusions. So you can correct that taking advantage of Taylor's law. I was talking today with, who was talking with me about portfolio effects? Lauren was talking with me about portfolio effects. Taylor's law is used in calculations involving Taylor's law is used in calculations of portfolio effects. Conservation of species. The bigger your variance for a given mean, the bigger the variance, the greater the risk of extinction. So it's been used in conservation theory. I'll show you it can be used for human populations. It's been used for infectious disease outbreaks. So let me give you some examples. This is joint work with Michael Hochberg at the University of Montpellier in France and with 2 students of his. Kirkpatrick and Ives published in Nature in around 2003 a paper saying, we expect that where there's competition, the slope of Taylor's law should be lowered. We decided to test that experimentally, so we took 2 species of bacteria easily cultured in the lab, Pseudomonas fluorescens, Serratia marcescens. We picked 1, 2, 3, 4, 5, 6, 7, 8 levels of nutrients, from very dilute nutrients to very concentrated nutrients, and we grew the bacteria 8 dishes of Pseudomonas alone, 8 dishes of Serratia alone, and 8 dishes of them together at each one of these 8 levels of nutrients. And this is the mean and variance of Pseudomonas when it's competing with the other guy, and this is the mean and variance when it's not competing with the other guy. And we found that we could not distinguish the slope of either alone versus competing or the slope of the 2 species. They were both 2. So we did not confirm that prediction of an effect of competition. Then we took Pseudomonas and treated it with phage. We wanted to find out what were the factors controlling the slope. We treated it with phage, we treated it with rifampicin, we treated it with phage plus rifampicin, and we left it alone. And in all these cases we found, well, a slope of about 1.9, less than 2, but not influenced by these biological treatments. This is a study we did in Black Rock Forest, which is a forest about 90 kilometers north of New York City. Bill Schuster is a PhD mathematician. Meng Shu he was a postdoc, he's now his own faculty member, a mathematician by training who came and worked with me. On this hillside, they divided a plot into 12, this field into 12 plots, 3 rows, 4 columns, and each plot, this is a plot, it's 75 meters by 75. This is 75 meters by 75. For each one of these plots, it was divided into 9 subplots, 25 meters by 25 meters, and we counted every tree in those plots. And then we took the means and variances. For each plot, we have 9 observations. We calculate the mean, for the subplots, calculate the mean and the variance, and we get a slope like that, and we get a slope like this after girdling some of the oaks. It's just to show you that this could come up in forestry as well as in bacteria. And finally, this is, I believe, the first demonstration of Taylor's law in human populations. This is joint work with Helge Brunborg, who is about to retire from Statistics Norway. Norway has 430 municipalities, which are organized into 19 counties, which are organized into 5 regions. And the Norwegians do not have a census. They have a population register. The police know where everybody is sleeping every night, which is good and bad, depending on what's happening. And we got this data from Helga from 1978 to 2010. So we arrange the data in the following format. We take the 19 counties down the rows and the years, how many people are in County 1 in 78, how many people are in County 1 in 2010. You may have data of this structure. This is an easy way for you to get hands on Taylor's law. So that's the data array. And then we calculate the mean and variance. I'm going to go back. Whoops. Mean and variance. So in this year, we can calculate the mean of those population densities and the variance. Mean and variance in the next year. Mean and variance in the next year. Each of those means and variances is one dot here. This is 1978, 79, up to 2010. And social science data rarely fall so nicely along a straight line. And we estimated this slope here. Pretty narrow. The slope you get depends on how you weight the counties. You can weight the counties equally, so each county is equal. You can weight them by area, and you can weight them by population size. And there are certain inequalities that you can prove. Well, counties are not given by God, so let's look at some other ways of aggregating the data. We can use the 429 municipalities instead of the counties. That's a finer spatial resolution. And again, we get a very nice linear relationship. Or we can aggregate the counties, and we get, again, linear relationships at the regional level. So that's the end of the empirical work. Okay? Now we're going to talk about abrupt biotic change in theories of Taylor's law. Any questions up to this point? Okay. So.
So yes. What would the population look like if it didn't follow Taylor's distribution? You know, like, do we have something to contrast it against?
Yes, we do.
What things look like in the film?
Good question. What would we expect? Well, if it didn't follow Taylor's law, if people were randomly distributed, totally randomly, then we would expect a slope of 1, and we don't get slopes of 1. 2, 4, 2.19.
Okay, but it would still be following it.
It would be a Taylor's law. Yeah.
Yeah.
Okay. So I have looked at some data, not yet published, on tribolium. And things can go like that. There's no apparent relationship. They're just scattered. That's one possibility. And I'm still trying to understand. That's a highly density-dependent system. Taylor himself investigated density-dependent fisheries models to see if they would obey Taylor's law. They do. So there's something special about the tribolium situation, which I don't understand yet. It's a good question. Thank you. Good. Thank you. Okay. So many theories of Taylor's law have been proposed. The Poisson distribution, I've told you already 2 or 3 times, gives you a slope of 1. The exponential distribution, in which the standard deviation equals the mean, gives you a slope of 2, an exponent of 2. If the standard deviation equals the mean, then the standard deviation squared equals the mean squared. But the standard deviation squared is the variance. So if the variance equals the mean squared, that's Taylor's law with an exponent of 2. I'm not going to talk about random sampling in blocks, but I am going to talk about exponential change of mean and variance and 3 examples. Suppose there's some parameter. It could be time, but it could be space, such that the mean m of t, this is mean, you're going to have to, m is for mean, v is for variance. The mean grows as an exponential function of time, and the variance grows as an exponential function of time. In that case, the variance grows as a power law of the mean, and you get that by simply substituting one into the other. Okay? If this is true only asymptotically, then asymptotically you get a Taylor's law. And more generally, if the mean is some function of the parameter t, whether that's space or time, and the variance is a power function of power law of the same function, then you have Taylor's law. This covers a whole lot of examples. In particular, if you have exponential growth here and exponential growth here, how do you get this beta? Well, you take the logarithm of both sides, so then you have log alpha plus beta t. Then you divide by the t, and you let t get large. This is called a Lyapunov exponent, and it's the way you calculate the beta. This is how you calculate the data. Delta you get by the Lyapunov exponent of the variances. So this is a formula for the exponent of Taylor's law. All of this stuff is in published papers in case anybody wants to get the details. No point in taking notes. I'll give you references. But this is a formula. It's the growth rate of the variance divided by the growth rate of the mean. That's what the exponent is. So now I want to give you a toy model of a population in a random environment. We start off with a population that has n0 individuals per unit of area. And we're going to make a climate model, but this is a toy climate model. So there are only 2 states in the environment, good weather and bad weather. You don't know about that here in Davis because you only have good weather. But where I come from, we have good weather and bad weather. And in good weather, the population density at the next time is the population density at the previous time times 2. So when you have a good day, your population density doubles. And when you have a bad day, your population density is reduced by 75%. You multiply it by 1/4. Okay? That's the whole model, except I haven't told you about the weather. And the sequence of weather days is specified by the climate model. And the climate is specified by the probability that tomorrow's weather will be different from today's weather. If that probability is 0, then you have infinite strings of good days or infinite strings of bad days. If that probability is 1/2, then the weather tomorrow is independent of the weather today. It just doesn't care. If that probability is less than a half, it means the probability of a change is less than a half, you have persistence. Good days are followed by good days, bad days are followed by bad days. In terms of power spectral density, if people have heard of red power spectra, such a time series has a red power spectrum. If lambda is greater than a half, you're more likely to change than to remain the same. So you're flipping back and forth, and that has a blue power spectrum. Okay, I've just explained what's going on this slide. We specify a climate by the probability lambda of a change of weather from one day to the next. So the weather changes with probability lambda, and it doesn't change with probability 1 minus lambda. And these are pictures. This is lambda equals 0.01. You have runs of good weather, runs of bad weather. Good, bad. This is independence, IID. This is blue weather. You're switching back and forth all the time. So here's the summary of the model. In good weather, the population doubles. In bad weather, it's multiplied by a quarter. Lambda is the probability, and we specify everything in matrices. These are the multiplying factors, which I call D. This is the probability transition matrix of the weather, from good to good, from good to bad, from bad to good, and from bad to bad. And this is the initial probability distribution. Assume equally likely to have good or bad weather. In that case, that's the stationary distribution. Now, you could just take this. This is a warning to graduate students and postdocs. You could just take this and put it on your computer and simulate it, and you will get the wrong answers. And I want to show you why, to warn you about overflow, underflow, and epsilon. Okay, so please watch this carefully. The maximum, does anybody here use MATLAB? How many people use MATLAB here? Okay, there are quite a few. Type in real max. It will tell you what is the largest number MATLAB knows how to represent. It's roughly 2 times 10 to the 308. Type in real min. 2 times 10 to the minus 308. The log of that is 1024, the base 2 log, and the log of this is minus 1022. If you calculate, if the weather, suppose you simulate the model for 1,025 time steps. Not unreasonable. Many people do 2,000, 3,000, 10,000. And the weather doubles your population size every time, and you start off with one individual, after 1,025 time steps, MATLAB tells you infinity, and none of your answers after that can be correct. If you put in only 550 time steps and you get 1/4 each time, 1/4 to the 550 MATLAB tells you is 0. Now there's no power of a positive number that is 0. That's a mathematical fact. So after 550 time steps, if that's the sample that you get, you're dead. Okay? But it's much more acute than that. That just shows you overflow and underflow. There's a quantity called epsilon, and I invite you to go look at epsilon. It tells you what's the minimum difference between two adjacent numbers in MATLAB. The epsilon for 1 is 10 to the minus 16th. If you take the logarithm of that, base 2, it tells you how many powers of 2 is less than epsilon. It's 52 powers. And how many powers of 1/4 is less than epsilon? 27 powers. So now I'm going to take epsilon, and I'm going to take 3 numbers in MATLAB. 1 plus epsilon over 4, and 1 minus epsilon over 4. And I asked MATLAB to calculate what's the variance of those numbers. And the answer is 0. That's wrong. MATLAB cannot tell the difference between 1 and this number, or 1 and that number, or the difference between this number and that number. But it's not 0. Be careful when you do simulations, because you can get the wrong answers. And I've had people write to me about the paper I'm going to describe next saying, your results must be wrong because I did a simulation and I don't get your answers. And they just don't know about underflow and overflow. There is a place for mathematics if you want the right answer. Of course, you can make mistakes in mathematics too. I've done that too. But I think you should be warned. I don't know the situation in R. Does anybody know if there's the same situation? There has to be the same situation. Same deal, right?
Well, actually, I don't know if it has to be, right? Because there are number systems where you increase the precision as you go.
Yeah.
So you can add more to it. And it's just taking an awfully long time to run.
Yeah.
You run out of memory.
You run out of memory. Okay. But,
Depends. I mean,
yeah,
that's
yeah.
where you can add memory. if you
But in routine R, it's the same, the day-to-day.
It's much faster.
Yeah, okay, okay. So you are warned. I've done my civic duty here. So we got to do some calculation, I'm sorry to say. We have to compute, I'm sorry?
You can change the matrix too, yes.
Of course, but I want the answer for all examples. And that's what I'm going to do here. I want all the examples at once. I'm greedy. So we calculate the nth moment, and it turns out you can write it, what does this mean, the pth moment? This is the population size at time t in that model that I just described, and we raise it to the p power, and we take the average. And it turns out this is a very simple linear algebra calculation. You take a row vector of ones, you take the D matrix with the multiplying factors, raise it to the pth power, multiply it times the transition matrix, raise that to the tth power, multiply it by a half, and multiply that. So this is now a scalar. This row vector, matrix, column vector. Put those together, you get a one number. You multiply it by this number, and that's the answer here. And that's in the paper. That's just simple, very straightforward calculation. And you can prove that the log variance minus b times the log mean tends to a constant. This is Taylor's law in logarithmic form, just taking the log of both sides. And here's the formula for b. b is the logarithm of the spectral radius of this matrix. R means spectral radius. You take this 2 by 2 matrix, you calculate its spectral radius. Every linear algebra student knows how to do this. It's a 2 by 2 matrix. You just take the determinant of the characteristic equation. You get the spectral radius, and I'm going to call that R2. You get the spectral radius of D times P, that's R1. And this thing is what A is, exactly, in all cases. So I'm reviewing now. In the special case, when lambda is 0, well, here's D squared P. Put lambda equal to 0. This disappears, this is 0, and this is 1 over 16. Okay? So you can calculate what it is. For both 0 and 1, you get a B of 2. That I could do by hand on my just pencil and paper. I wanted to know what happens when lambda is between those two. So I actually had to do some work, and I calculated the explicit formulas for B for all lambda between 0 and 1. And there is, in here is this formula, and if you unfold this, the R2 is here, and the R1 is there. So it's just evaluating numerically. Instead of simulating, I'm simply evaluating the formulas numerically. And I was surprised when I got this graph. This is the surprise that I'm talking about. So for lambda equals 0, lambda, remember, it's the probability of a change in weather. We get a 2 here. This is B. For lambda equal to 1, we get a 2 here. In between, there's a singularity, not at independence, which is a half, but this B goes up to positive infinity at 3/5, and then comes back from negative infinity there. That was surprising to me. So I said, first of all, that must be wrong. And I checked my code, I checked the mathematics. It's right. So then I said, why? So I looked then at the growth rates of the mean and the growth rate of the variance. And what happens, in retrospect, I should have been smart enough to see this, but I wasn't. What happens is B is the ratio of the logarithm of these two growth rates. When this is in the denominator, when the growth rate hits 1, what does that mean? That is a stationary population. It's a population that ain't growing and it ain't shrinking. It's just stationary. The logarithm of 1 is 0. When you get a 0 in the denominator and a positive quantity in the numerator, you go to infinity. So what happens is, as the rate of weather change, lambda, goes from 0 to 3/5, the rate of growth of the population goes down until it becomes stationary. At that point, B is not defined. Taylor's law fails. It's relevant to your question. And if you're plotting variance as a function of mean, it's all over the place. No relationship. So that's what's going on here. Then it comes back from negative infinity because the population is shrinking. A singularity in B in the multiplicative Markov process occurs in general, not just in this example. And I give there the mathematical assumptions under which that's true, but it's true in general. I'm going to skip that. A singularity in B occurs in other population models that obey Taylor's law. And I'm going to take two very familiar ones because it's surprising that this has not been noticed until this year, because these models have been around since the 19th century. The discrete Galton-Watson branching process. Galton was the guy, was a cousin, I think, of Darwin, who wrote a book called Hereditary Genius, and he was interested in the extinction of names. Why is it that some family names go extinct? He invented a mathematical process called the branching process, or the Galton-Watson branching process. Each individual of generation T independently has a stochastically distributed number of offspring in generation T plus 1. The mean and the variance are M and V of the number of offspring per individual. And these are two formulas from Bartlett in 1955 for the mean and the variance as a function of time and of M and V. The variance here has two terms, M squared and M to the T. Forget the minus 1. When M is big, clearly this term will dominate that, and that we can forget about. And you get a Taylor's law with exponent 2. When M is less than 1, and you take multiple powers, this vanishes twice as fast. Like 0.8 squared is 0.64. It's even smaller than 0.8. So you get an exponent of 1. So what happens is, if the average number of offspring per individual is bigger than 1, Taylor's law holds with B equals 2. If it's less than 1, Taylor's law holds with B equals 1. If it's equal to 1, it's not defined. The formulas do not work. The calculations don't work. So as M moves smoothly from greater than 1 to less than 1, you get an abrupt shift from 2 to 1 in the Taylor's law. And birth and death processes. Assume a birth rate lambda per individual, a death rate mu per individual. Each individual has a probability mu of dying in the next infinitesimal piece of time, and a probability lambda of giving birth to another individual, like bacterial fission. Again, the formulas are given by Bartlett in 1955. Here's the mean as a function, whoops, sorry about that. Mean as a function of time, the variance, and again there are these two terms here. This is going to be a squared term, this times that, but this times that is going to be a linear term. So if you do the calculation, B is 2 if lambda is greater than mu. What does that mean? means the population is growing because the birth rate exceeds the death rate. If lambda is less than mu, the birth rate is less than the death rate, the population has to go extinct, and you get a 1 here. And it's not defined at that transition point. And here, my colleagues, Zhang, DeAngelis, and Zhang did some simulations, and this time they did it in a reasonable way. So what we do is we fix lambda at 0.01, and now we vary the we fix the death rate at 0.01, and we move the birth rate right and left, and you get a singularity there, just as we predict. The blue line is the theoretical calculations, the circles are the numerical simulations. Generalization. In Markovian multiplicative, branching, and birth and death processes, a singularity in B occurs as the population passes through the stationary state from increasing to decreasing or vice versa. And I want to thank Alan Hastings for publishing this paper in Theoretical Ecology. I greatly appreciate his sagacious judgment about whether it was publishable. Could an approaching or actual singularity in B serve as an indicator of the passage of population dynamics through a stationary state, forewarning of outbreak or extinction? In other words, I'm turning this around. If B goes off the charts, that tells us that our population may be moving either to an insect outbreak or to an extinction. We can turn it around and use this as an indicator of growth or decline in population. How general is the finding of singularity in B of Taylor's law? That's for you to decide. Could a microcosm experiment or field observations demonstrate the singularity or precursors of singularity in Taylor's law? This is an empirical question. Thank you very much for your patience and your interest. Alan.
So on your last slide, the
Yeah.
question, Drake and Griffin did this experiment with Daphnia where they remove food.
Tell me. I don't know.
They removed food and they were looking for early warning signs, and they claimed they found them. Of the saddle node thing, the only problem is it's not a saddle node, it's an exchange of stability, it's passing through. And so the data may be there, but just look at some.
So Drake and who?
Griffin. All right, it's John Drake, was published in Nature.
Thank you. I will look into that.
They didn't, I mean, like many, they had a number of replicas, but not that many, and that's part of the problem.
Yeah, okay. So you have to have pretty good estimate, but worth looking into. I wasn't aware of it, so thank you very much. Drake and Griffin. Griffi or E-N?
E-N.
E-N, okay, good. Thank you. Yes, sir.
So, you're looking at models without density-dependent feedbacks.
Right.
And if you have models with density-dependent feedbacks, you'd expect the growth rate always to be critical, right, at 0 in the stationary state.
Yeah.
So, if you think natural populations often are sort of in that stationary state, wouldn't you expect there not to be a Taylor's law? So,
Very good question, but if you remember, you can have stationary state in the long run at different levels with different quantities of associated variability. So Taylor actually asked your question and did some simulation studies of chaotic population models. I think he used a Ricker model for, the Ricker fisheries model, and showed as you tune the parameters of the Ricker function, recruitment function, you get changes in the mean level and you get changes in the variance, and those do satisfy Taylor's law. And that's a paper of his, I think, Journal of Animal Ecology. I certainly can get the reference, but so even though it's stationary in the long run, you have different levels of mean and different levels of variance. Good question. Any other questions? Yes, Jim.
So this applies to portfolios and raindrops and aphids and so on and so forth. But with respect to aphids or insect distribution, what does this tell us about the biology that we wouldn't know just by thinking hard about it, or some other statistical analysis.
Without further information, Jim asked, what does this tell us about the biology? And my answer is, without further information, it tells you much less than Taylor thought. And with further information, it tells you much more than you knew before. So to be specific, if you don't have any idea of what the mechanism is of population dynamics, this ain't going to tell you. Because you can get Taylor's law from so many different models that you cannot infer back to mechanistic process from the parameters or the form of Taylor's law. So that's less than Taylor hoped for. On the other hand, if you know that this is a multiplicative process, you get information about the details of that process from the parameters of the Taylor's law. So you have to do some work to squeeze juice out of this model. You have to know something about the details of the dynamics, and then you can get good things out of it. I didn't go into the detail on the forestry model, but we showed, we proposed a dynamic model. We tested it in detail by looking at 15 censuses over 75 years of how the number of trees on each plot changed from one 5-year period to another. And that satisfied the assumptions of the model, and then we're able to make statements about the mean and the variance and what to expect going forward. So you have to do some work. Marissa.
So you're suggesting that a breakdown of your Taylor's law can be an early warning signal. Is it possible to get a breakdown of Taylor's law, say from something like external forcing or anything else like that, basically a false positive early warning signal when you're not approaching that singularity of going from balanced to either declining population or exploding population?
It's a very good question. I haven't thought about that in detail. So my immediate response is I would guess you could have Taylor's law disrupted by hitting the thing with a hammer, by some other disruption that really knocks down all the means but doesn't change the variances or knocks the variances out of kilter. That's an immediate response, and I attach a confidence of 0.1 to that. And after I think about it later, I might have a better thought. But that is my guess based on sheer plausibility. But it's a good question, and I don't know the answer for sure. Other questions? Yeah.
Just for Yogs, how do changes in magnetic flux look at different time scales? You know, when the Earth's changing.
Yeah.
Yeah.
So I've actually been interested in that. You know, the orientation, if you look at seafloor spreading centers, the stuff comes up out, and while it's molten, it adopts the magnetic orientation of whatever the poles are at that time. The poles have been flipping back and forth about every 2.5 million years for quite a long time, as long as there have been oceans with seafloor spreading. And you can read the historical record of which way was the North Pole pointing at that time by looking at the magnetic orientation at greater and greater distances from the seafloor spreading. That's what you're talking about, right? Okay. That, to the first approximation, as far as I know, is like an exponential system with two states. It seems to, the inter-transition interval seems to be roughly exponentially distributed. So it runs along for a while, and then the thing flips and goes the other way for a while, and then it flips and goes back. And the rate of flipping seems to be more or less constant over time. I'm not sure what the connection with this would be, but it's an interesting process. Yeah. Oh, please.
Yeah, you were talking about sort of continuous change in environmental variables, but really what happens is when, say, the mean value of an environmental variable, whether it's a storm or a sea level rise, increases, we also see the increase in magnitude and frequency of extreme events.
Yeah.
And so I'm wondering, is the power law, it obviously refers to the magnitude of variance as a function of mean. How about something like the frequency of sort of extreme events, I mean, a probabilistic thing, but does that scale in some knowable way with mean? And would that be sort of a better focus of prediction? Because really that's what flips natural systems from one condition to the other. It's really sort of an extreme event rather than the mean value.
It's a very good observation. And so suppose, and I actually wrote Jim Hansen about that, and I have not yet got an answer, but he's got other things to do. But, okay, this is some variable like temperature. And we have a frequency distribution, let's say a normal distribution, a bell-shaped curve, and extreme events are things that are out, a certain number of standard deviations. When we shift the mean, as we are doing, so mean temperature globally has gone up. Question, are we changing the variance at the same time? If we are increasing the variance as Taylor's law would predict, then the extreme events are going to be much worse. As you shift it, if the mean goes up and the variance goes up also, the bad things at the tails will be amplified, not only by the shift of the mean, but by the enlargement of the variance. So it's crucial to know whether the variance is going up. And I haven't found evidence to address that. But the theoretical question is very important. We don't know whether the variance stays constant while you shift the transition or the variance goes up as you shift it. And that's an empirical question. I'd love to, that's a great important question. Thanks very much. I've enjoyed the conversation.